All right, let's just jump right into this. I want you to picture rolling two standard six-sided dice. You know the drill, right? They settle, you add the numbers up. It's something we've all done literally hundreds of times playing board games. But here's a question for you. What is the absolutely most likely total you're going to get? Like, if you had to bet everything on one specific sum to maximize your chances, what number are you picking? Think about it for a second, because framing it this way is actually the very first step in our mathematical investigation today.
So, welcome to The Explainer. Today, we're looking at how seemingly random events, like, say, a roll of the dice or dropping a marble, actually follow these beautifully predictable mathematical rules. We're going to take a journey through probability, starting with stuff you probably already know and pushing into some truly fascinating theoretical territory.
Here's our agenda for today. First, we've got the dice sum puzzle. Then we'll move into the probability drop game, and finally, we'll wrap up with Buffon's needle experiment. Let's get to it!
Okay, part 1, the dice sum puzzle.
Now, to truly understand what's happening when we roll two dice, we need to map out every single possibility. If we put this on a 6x6 grid, we can literally see every combination. You've got die 1 on one axis, 1 to 6, and die 2 on the other. Inside the grid, we just add them together. When you fill out the whole thing, you get exactly 36 possible outcomes. But look at the pattern that emerges here. Right down the center diagonal, we have a clear winner. A total score of 7 appears way more frequently than any other number. You roll a 1 and a 6, a 2 and a 5, a 3 and a 4, and so on. It's pretty cool to see it laid out like that.
So the crucial takeaway here is that out of those 36 possible outcomes we just mapped out, exactly 6 of them give you a total score of 7. Mathematically, the probability of getting this most likely total is 6 out of 36. And, when we simplify that down, we get exactly 1/6. If you guessed 7 earlier, hit the nail on the head. But hey, why stop at standard dice, right?
What's really fascinating is how this pattern scales algebraically. Mathematicians absolutely love taking a specific case and generalizing it. So imagine we aren't using normal 6-sided dice anymore. Imagine an 8-sided die, a 10-sided die, or just some totally theoretical m-sided die. If we roll two identical m-sided dice, our total number of outcomes completely shifts. Because we have m possibilities on the first die and m possibilities on the second, the total outcomes will always just be m squared. So two 8-sided dice, 64 outcomes. Two 10-sided dice, 100 outcomes. Makes sense, right?
And we can push this logic even further. What if the dice don't match? Say we mix them up and roll an m-sided die right alongside an n-sided die. Let's just say m is greater than n. Well, we can logically figure out the total number of outcomes using that exact same principle. You literally just multiply the number of sides together. So the total outcomes will always be m times n. It's such a brilliant way to see how super simple counting rules can scale right up into algebraic formulas.
Moving right along to Section 2, the probability drop game.
The physical setup here is wonderfully simple, but it's incredibly effective for studying probability. Just imagine dropping a little red marble down a chute. On its way down, it hits a triangle divider. Now, at this point, it has to make a choice. Well, I guess physics makes the choice, but it's going to bounce either left, which we'll call L, or right, which is R. After bouncing its way through these dividers, it finally lands in one of the numbered trays waiting at the bottom.
So if we look at a really small version of this game, with just 3 trays down at the bottom, we can actually start tracking the routes. Like, how does a marble end up in the middle tray, tray 2? Well, it requires very specific routes. If it goes left, then left, it just ends up in tray 1. But to hit the middle, it could bounce left, then right, so path LR. Or it could bounce right, then left, path RL. As we expand the game, adding more rows of dividers and way more trays at the bottom, the number of distinct routes to those middle trays just absolutely multiplies.
In this setup brilliantly illustrates one of the most famous structures in all of mathematics, Pascal's triangle. If you start digging into the probabilities of the marble landing in each of the different trays, especially in bigger and bigger versions of the game, the frequencies perfectly mirror Pascal's triangle. In this array, every number is just the sum of the two directly above it. The number of pads a marble can take to reach a specific tray corresponds exactly to the numbers in the triangle. It is literally a stunning physical representation of binomial expansion playing out right before our eyes. No way, right?
Okay, for our final act, Section 3, Buffon's needle experiment.
Now we're turning our attention away from standard games and looking at a genuinely fascinating physical challenge. This was devised centuries ago by a French mathematician known as Lecomte de Buffon, And what makes this experiment so special is that it bridges the gap between basic probability and these really advanced geometric constants, all using nothing but a flat surface and some everyday objects.
Here's how you can actually recreate this genius experiment yourself. First, take a match. You'll want to cut the head off to keep it perfectly straight and measure exactly how long it is. Then, on a big sheet of paper, draw a series of parallel straight lines. The absolutely crucial thing here is that the distance between each of your lines has to be exactly the same as the length of your match, okay? Next, you grab 10 of these identical matches and just drop them totally randomly onto the paper. Finally, carefully count exactly how many matches cross or even touch any of the lines. You just repeat that 10 times until you've dropped 100 matches in total.
Now, because we're looking at continuous probability here, we need a lot of data. So to track our results, we log the total number of drops as n, ranging from, say, 100 all the way up to 1,000. We log the number of matches that crossed a line, and then we calculate p. That's the probability of a match crossing a line, which is simply the crosses divided by the total drops. Taking that probability p, we then calculate a very specific mathematical ratio, 2 divided by p.
So, as you gather all this data, plotting these cumulative drops up to 1,000, calculating your probability p, and crunching that final formula of 2 divided by p, you're left with a truly profound mathematical cliffhanger. If you plot a line graph of n against 2 divided by p, you'll see the line starts to stabilize. It actually hones in on a very specific, deeply famous numerical value. I'm not going to spoil it for you right now, but I seriously challenge you to grab some paper, drop some matches, and answer this final question for yourself. What value does 2 divided by p magically appear to get closer to? I promise you, the answer will absolutely change the way you look at random chance forever. Anyway, thanks for exploring the hidden architecture of probability with me today.